Hello students, it's Dr. Church, and we're going to start a new unit today on mechanical waves. So let's just jump right in and see what are waves. Well, that's a very familiar wave to everyone. That's a wave that we would see on the big island of Hawaii or Maui or somewhere like that. But it's that's a big wave, and those waves carry lots and lots of energy. So what is a mechanical wave? A mechanical wave is a disturbance that carries energy from one place to another. As a wave passes through the ocean, it in fact is not moving the water particles to another location, rather than just they vibrate basically up and down, but it's the mechanical wave is actually carrying energy, not the matter, as it were. So there are different types of waves. There are certain types of waves that don't need a medium in which to move. Mechanical waves do. They have to have a medium in which to move. It's why you can't hear sound in space, because there's no air in order for the wave to move. But light is a special type of wave. It's electromagnetic wave. Light, this is a more complicated discussion in physics and quantum mechanics about the photonic nature, the particle nature of light, and the wave nature of light. It has what's called a wave particle duality to it. But mechanical waves require some sort of medium, be it a solid, liquid, or a gas. That mechanical waves can transfer energy through those mediums. A mechanical wave is created when a source of energy causes a vibration to travel through the medium. So I have a little video here that's kind of neat that you can watch. This is a guitar that is actually being played, and the videographer has put some type of a phone or a video recording device underneath, and as they pluck the strings, you can see the waves are moving along the strings. And you'll notice that the larger strings, the low E, the waves are longer, and once they get up to the higher strings, so you got E, A, D, G, B, and E, the high E, you can see how the waves get closer together and the vibration frequency picks up. And we'll learn more about that later, but that's kind of an interesting thing to see as the waves move along the strings. And the guy's a pretty decent guitar player as well. So that's the creation of mechanical waves. Is in the case of a guitar, the energy comes from the fingers of the guitar player as they pluck the string. Well, there are three types of waves. The first type one, is what's called a transverse wave. And that's essentially what you were seeing there. Waves in a medium that moves at right angles to the direction of the wave. If we see those waves move up and down, if the person holding the string were to move his or her hand up and down, then the vibration is transverse. It's in direction perpendicular to the wave. The wave is actually moving. One second. For some reason that was white, and you can't see the white on that background, so we're going to make that red, and we're going to make it just a little thicker so we can see it. So the wave is actually moving in this direction. It's moving that way, but the movement of the string is actually moving in this direction. Okay, it moves up and down. So that's why we say that the waves are transverse. The direction in which the energy moves is away from the source of vibration or the source of energy, but the actual medium, in this case a string, is moving transverse, or at 90-degree angles, at right angles to the direction of the wave. So that's the first type of wave. It's called a transverse wave. The parts of that wave is labeled as, you've got the crest. That's the highest point of the wave. Okay, that's the crest. Then you have the trough. Sorry, I always do that. You have the trough, which is the lowest point of the wave. Okay, that's the lowest point of the wave. And then you've got what's called, in this case, they're calling this the rest position. That's a node. And it's interesting about the wave, while the trough and the crest are moving up and down at right angles away from the wave, if depending on the height, the amplitude of the wave. But this position right there, that one little position, if we were to zoom in on that position right there, it is actually at rest. It's not moving at all in a transverse wave. Well, there's a second type of wave, that's the compressional, or what's called the longitudinal waves. And in this case, the waves in which the medium actually move parallel to the wave. They move in the same direction. So let me go ahead and let me grab this arrow here. Sorry, I'll just copy that arrow and stick it on here. So in this case, the wave is actually moving in this direction, right? So you can see that there is indicated by that arrow. And in this case, the medium is actually moving in the same direction as the wave. This is a spring. In a classroom, we could demonstrate this, and you can actually see those waves moving back and forth fairly easily. And so the medium is moving back and forth, and the wave is also moving back and forth. So that's longitudinal. It's going along the length or the long axis of the spring in this case, and that's a compressional wave because the medium is actually compressing and elongating, compressing and elongating. There's the compression zone in the wave, and then the refraction zone. That's where it goes furthest apart. The compression zone is where it comes closest together. If we looked at the particles, like this is an example of a sound wave moving within a tube, and we could look at the air particles in the tube, similar to a spring, there would be compression zones where the particles move closer together, and then what's called rarefaction zones where the particles are separated further apart. My voice is actually, my vocal cords are vibrating. They are resonating within my vocal cavities, my head, my sinuses, and that's creating a wave that's moving the air particles in front of me back and forth, which then is picked up by the microphone. That's translated into an electrical signal, and then your speakers are actually moving the waves back and forth, and then that's going into your ears. If you're wearing earbuds, you have a very, very tiny diaphragm inside those earbuds, which are moving back and forth, very small waves inside of your ear that you can clearly hear. There's one final type of wave, and that's called a surface wave, a wave that travels along the surface of two mediums. And so this is actually the combination of a transverse, right? The transverse wave and the longitudinal wave, or the compression wave. And so the surface wave is actually, when you add those two things together, you get this sort of circular motion. The circular motion is like a bob moving up and down on a fishing line that's anchored by some kind of a weight. It's moving up and down and back and forth, and when you add those two things together, you get a circular motion. So there's your your three types of waves. A bit of a definition about the waves. These are mechanical waves. Mechanical waves are, every time you hear, you're experiencing mechanical waves. Vibrations in all kinds of mediums are mechanical waves. And we'll go on and talk a little bit more about properties of waves and a little bit about that. And it's really a fascinating study of physics. If you're a musician, if you're into audiophonics at all, or audio sounds and sound systems, knowing and understanding acoustics and the way that waves work is really critical to that. And people do that. People that travel with bands set up sound systems in stadiums that work with the electronics part of it, and the design and manufacture of all kind of acoustic equipment, musicians. This would be a fascinating area of physics and study for you guys. So I hope this little introduction into waves has been a good educational learning tool for you. Remember, our class values integrity, respect, responsibility, and I hope you learned something today. I'll talk to you soon.